start the
Sorry for my
recording.
horrible English.
It doesn't matter. It doesn't matter. The important thing is the mathematics, the deep learning, and everything. All right. So I was, putting down the list as Margherita, Filippo, Elena, Francesco, and Devashish. But if you have a different order, we're gonna be here, so it's okay with me. Do you have any reason to change the order? No. All right. Are you
I need to present after Francesco because it's the second part of the same presentation.
Duly noted. Okay, so now we listen to Margherita. You can share the screen and start with your presentation. Remember, it's between 15-20 minutes, and I may interrupt you to ask for explanations, okay? So don't worry about that.
Okay. Okay, let me share my screen quickly. Can you see it?
Yes, I see it very well.
Great. Well, good evening, dear Professor Fiaressi and colleagues. My name is Margherita Mishina, and today I'm going to tell you about graph attention networks. I plan to briefly recall how the message passing mechanism works in GNN and how GAT modifies it. Then I will dive deeper into the application of GAT to an edge prediction task in my current study. Okay. Well, as we remember from the lectures, graph neural networks implement a message passing mechanism that allows us to learn latent node representation, considering their aggregation from nearby nodes. In this paradigm, we have three main steps shown in the formula and list at the top of the slide. And let's assume that H in the formula is the embedding of a node at step K. Then first, each node receives messages from neighbors and applies a message function denoted by phi in the formula. After this, for each node, we aggregate all messages via the permutation invariant function, such as sum, mean, max, and so on. And finally, we apply a nonlinear update function, here is gamma in the formula, that combines a node's own hidden state, this, with the aggregated messages from the neighbors. And all this gives us a new hidden state, new embeddings for each node. So practically what it means, as you can see in the left picture here, we have initialized the current state of the node at step K. And after the message passing, what we actually is expecting to see that on the step K+1, for example, the embedding of node 1 will include some information about its neighbor's features, colored pink in this picture. That's how message passing generally works in graph neural networks, and graph attention network adds to this process attention mechanism that allows us to consider the different importance of neighboring nodes.
I'm sorry, Margherita, I have a question. So you write in EJI, this is a bias in the formula. What is it, this EJI? There is like a EJI, this. So in the message passing, there is the phi, and then the node embeddings, and then there is this EJI. What is it?
This is the central node. I mean, HI, for example, this is the one, that's
No, there is the letter E, the letter EJI. Is it the central node?
What exactly do you mean? EJI, yeah, HE. This is for example, the central node that, for example.
Okay. So you define differently the central node. Okay.
Yeah, actually, I've just take this formula from PyJ geometric. I find it pretty clear.
No, I don't question where you got it. I just wanted to understand the meaning of all the symbols there. Okay.
Yeah.
Okay, keep going.
Okay. The idea of attention mechanism was proposed by Veleskovich in his paper about graph attention networks. And he suggested the formula. He suggested basically multiplying messages from neighbors by normalized attention coefficient, alpha AJ. And to compute these coefficients for each pair of nodes, he fed nodes embeddings HI and HJ, as we see here, to a feed-forward neural network, then applied Licky-Relu activation function, and then normalized it over the local neighborhood with exponent. And the latter work actually have proposed some modifications of this attention formula, just to consider H features as well, as you can see here, EIJ. And as a result of applying this attention mechanism, we can say that some neighbors will have a more significant impact on the node embedding of a central node, which is green in this picture. Moreover, to stabilize the process, Veleskovich proposed the multi-head attention mechanism, and it basically means that we need to calculate attention coefficients several times and then either concatenate or average results. According to the paper, it's recommended to use the concatenation on hidden layers and average on the final layers. So,
no, okay, very clear, very clear.
Yeah. And let's move on then to the advantages of using GAT. First of all, it has to be said that it's very computationally efficient, since it might be easily parallelized. Also, when computing attention coefficients, we don't need to operate on the information of a whole graph, since we calculate it only for local neighborhoods. Next, as we already discovered, it allows us to assign different importance to neighboring nodes, which is really great. And last but not least, GAT works on both transductive and inductive learning. And just a little reminder, since I'm going to come back to this later, in transductive learning, we observe all the data beforehand, both the training and testing data sets. While in inductive learning, we observe only the training data and apply the learned model to a data set that we actually have never seen before. That's the main difference between transductive and inductive learning.
I'm really interested in what you're saying, because so I am familiar with the autoencoders. So transductive learning, is it you know, like autoencoding type of learning?
Yeah.
Very nice.
Kind of.
We couldn't do it during the course because, of course, we didn't have time, but it is very interesting. So let's keep going. Okay.
You're a bit interrupting.
Yes, keep going.
Okay. Okay. Yeah, the next slide. And before I dive deeper into my study, I need to mention that in practice, we encounter 3 types of tasks in a graph, and you can see them on the slide. That's graph level task, node level task, and edge level task. In a graph level task, our goal is to predict the property of an entire graph. And for example, for a molecular represented as a graph in the left picture, we may want to predict, for example, its property. Here, namely, if it contains 2 rings or doesn't. Node level tasks are usually concerned with predicting the identity of role of each nodes within a graph. And a classical example of node level predictions problem can be shown in famous Zag Karate Club, where we need to classify to which group each club practitioner belongs. As a result, in this picture, we can see that nodes of different groups are colored red and gray. The remaining prediction problem is graphs is edge prediction. In this case, we actually aim to predict the relationship between 2 nodes. We may want, for example, to predict which nodes in a graph share an edge, or what the value of that edge is. For instance, in the picture, we see predicted relationship between Karate Club practitioners. They are fighting, watching, and standing on. And one important comment here is that if we wish to discover connections between nodes, initially we have to consider a fully connected graph. It's very important. And after we get the predicted value for each edge in a fully connected graph, we can prune them to arrive at a sparse graph. And well, one may notice that it can cause sometimes some computational difficulties, especially when we're working with massive graphs.
Yeah, Margarita, I kind of disagree on this little point, because it's true that if you want to predict the edges, you may think that fully connected is the way to go, but sometimes it's not, in the sense that you may decide some criterion where you put an edge. For example, you can try the homophily criteria, right, when the features are similar, because doing fully connected very often is not practical. I mean, with the baby graph of Karate Club, yes, of course, but like if you have some real life graph, it will be practically impossible to do what you say. You understand the problem, right? I mean, if you put all edges, it will be difficult.
Yeah, that's actually the problem, but could you please repeat some examples why we can, what solution we can use in this case?
So no, it's not my solution, it's what people do. So what people tend to do is the homophily criteria. That is, you take the features on the nodes and you compare them. So if the features are similar in some way that you decide, then you connect. If they're not, you don't. And then you try to predict edges with that.
Yeah, I understand you. And actually, that's a very good decision, but we can do this in our study that we actually working on. And we are,
I'm looking forward.
We have to
go.
Yeah,
yes.
And we have to work with fully connected graph.
So you may have a different reason. So I was just doing an observation, but of course it depends on the problem. Yes. Okay, go.
Yeah, of course. Thank you. All right. It was part of fundamental theoretical part. And now I'm going to share with you how exactly we use graph attention network to predict human mobility in city. Very relevant question nowadays. The task formulation is the following. We want to predict how many people living in each residential building interact with service facilities in a city, such as kindergartens, schools, polyclinics, and so on. Considering that we know the demand accumulated in each residential buildings and capacity for each facility, also distances between all of them, and observed actual interactions, but only for one part of a city. And for the rest parts, we have to predict it. This is basically an inductive problem and an edge prediction task. This picture on the left side of the slide, the small part of a bipartite graph that we consider, and it's fully connected. As I mentioned before, we need to consider fully connected graph to consider all possible, all potential interactions, all possible edges. In this case, we can't omit some edges because sometimes people from residential buildings can travel for a long distance to meet the demand because they don't have services, they don't have facilities near their own neighborhood. So in the entire fully connected graph, we have more than 20,000 nodes and more than 20 million edges Yij, for which we need to predict the number of people living in building I and using facility J. I hope that the task formulation is clear, what we need to do.
No, very clear. Yes.
So to do this, we use an approach that combines a graph attention network and a multi-layer perceptron. Specifically, we use two layers GATs to learn latent representation of the node based on spatial relationships in a graph. Then embeddings of each pair of nodes are concatenated and resulting vectors are fed into two 4-layer multiple perceptron. The hidden layers.
Can I ask you? So from the graph, it seems that you are doing encoding with the graph attention network. Then it is the decoding, right? It is multi-layer. Do I understand it right?
Yeah, exactly.
Okay, thank you. Go ahead.
The hidden layer of MLP recombines nodes embedding in a nonlinear way, and the final layer makes a prediction. Actually, I find a similar approach in the paper that I attached to the slide, but they used gradient boosting instead of MLP.
Okay.
And it would be actually interesting to compare our two approaches a bit later. Speaking about model performance, I wasn't sure how much information I could show on the slide because we're in the process of writing and submitting the paper about this topic to the journal. But anyway, I would like to mention that we managed to outperform the state-of-the-art human mobility model, namely doubly constrained gravity model. And we also discovered that nodes representation learned by GAT contributes significantly to the accuracy increase in comparison with architecture that uses only MLP layers. And basically how we managed to learn such a huge graph, as I mentioned, it's fully connected. We decided to do it iteratively with splitting our huge graph on several bunches and learn it iteratively. And that's helped us to solve this actually difficult problem. So yeah, I hope that our paper will, with all the experiment, will be available soon. And yeah, that's all that I wanted to present today. Thank you so much for your attention. Feel free
very exciting
to ask any question. Yeah.
Yes.
Thank you.
I think it's extremely exciting. I absolutely want the paper because we're doing something not edge prediction. We're doing, the typical node label prediction, but this seems very relevant. So please send me the paper when it is ready. Okay, don't forget it.
Yeah, definitely.
So does anyone has questions or comments? Okay. You answered to all the questions. No, I think it was really excellent. I enjoyed your presentation. Thank you very much, Margherita. And please remind me of everything I have to do bureaucratically to, conclude the successful pass of these credits. Okay. So, but it's on you. Remind me because I'm, very pushed by many directions.
Yeah.
Right.
Yeah,
and,
certain. And thank you for very useful and interesting comments.
Okay.
I will consider this.
No. So the next is Filippo. Margherita, you cannot leave, right? All of you should be staying here because it's part of, the exchange of information. And also, I think that you guys got to know each other. We will put the slides, if you, Margherita, send them to me on the website and with your address, email address, so you guys can talk to each other. Perhaps now you're a bit shy, you're like, I don't want to ask questions. So, but totally, this thing should be interactive, okay? So, Filippo, go ahead. It is mostly embarrassing because Filippo is speaking about a paper of mine. So, let's see if you find errors, right?
I can only say that it is a good work.
Okay.
Okay. I try to share. So
sure. You have like 15 minutes, between 15 and 20, because I interrupt a lot. So. Okay, great.
Can you see?
Yes, we see it very well.
Okay. So in the following slide, I will present a work of Rita Fioresi and Janko Petkovic, in which a strong connection between our visual system and CNNs it is established in order to make the CNN robust against a large variation of light. So in my slides, I will present a briefly introduction, then I will give a presentation of our low visual system from an anatomical point of view, and then I will describe the mathematical model. So we have all the elements in order to link this visual system anatomy with a classical CNN, that is the Linet 5, and in order to introduce a module, a sort of preprocessing module made by free convolutional layer that adds robustness against the light variation. And then at the end, I tried to implement this preprocessing module to the CNN that Fernando presented to us during our lessons. And so I don't know if I have enough time, but
Ferdinando, not Fernando. He gets upset.
Ferdinando, sorry, Ferdinando.
They got wrong his name.
This presentation. Okay.
Right.
So the studies of visual perception gives us similarities between CNN architectures and the modeling of the visual pathway. And in these works that are reported in this slide, it is established a connection between the functioning of V1 cortex and a classical CNN. So, because V1 cortex, it is not the first part of our visual system, and because CNN has a strong similarity with this part, and with the first layers of this classical CNN, this analogy suggests to the authors that maybe an additional preliminary convolutional module can be added to this classical CNN in order to add the effect of also the effect of retina and LGN. So I will speak about the low visual system anatomy, and especially I will speak about retina. That is the one that I'm lighting with my arrow, and LGN and the primary visual cortex. So I want again highlight the main idea. A lot of classical CNN shows the ability of locate and identify, for example, directions in first layers. So if we know that the primary visual cortex has the same ability in our visual system, we can think that maybe we can implement in our architectures some additional layers that can simulate the functioning of retina and LGL in order to complete all the process of visual system, and in order to improve robustness against light variation. That is the problem that retina faces. So this is a 3D representation. We have retina, LGN, this little part of our brain, and the V1 cortex. And now we will focus on retina.
Yes, so Filippo, I just wanted to clarify that our paper with Petkovic is concerned about what is called the low visual system pathway. Yes. Because as you correctly show in this picture, when we view an image, our brain has many areas that are involved. So for example, the cortex, which is V1, is the one that detects the border of an image. But then there are the sequence, the other cortex, layers of the cortex, you know, V2, V3, and so on, where we elaborate the image, right? So this we are not interested in our paper. We look only at the V1 cortex, which is the first one in our brain receiving the signal. So in some sense, it is the first layers, right? So you receive the image that got projected, and this is also for the others that they may think, you know, that the cortex V1 is where all the image is understood. No, it's only where we understand the borders, right? And then the rest, the form, you see, you show the form, you show the color, you know, these are all different issues. They come in different parts of the brain. That's my observation. Okay.
Yes, yes.
So keep going. Yes, of course.
Then V1 cortex behaves like the force convolutional layers that
exactly,
identify and locate specific direction and orientation of the image.
Yes. But
so the
does
idea
not
is to
understand.
add.
Yes.
Thank you for.
No, I was just clarifying, but go ahead. Yes, of course.
Yes, so we focus on the following structure. Then we have retina, that it is essentially consists of photoreceptor cells and these other cells that measure intensity of light and are responsible of gain tuning effect, consisting in border enhancing and ability to react to the large variation of global light of an image. Then we have lateral geniculate nucleus that receives information directly from retina, and then it gives us a further smoothing effect on the signal. And it is linked directly with the primary visual cortex, that is the area of the cerebral cortex that is the first processing step, and it is receptive to some feature of light and specific direction. So this is a scheme that we will see later, and now we can introduce the mathematical model for this specific part. In particular, in the article, it is modeled the retina and V1 cortex, because LGN may be approximated for simplicity with the last processing step obtained from retina. I think that I can say this fact. Maybe I can ask a confirmation to Fioresi.
Yes. So we are not interested in what really happens in the lateral geniculate nucleus. Of course, there are other people studying it. I mean, we only concentrate on retina and cortex. This is our modeling.
Because V1 cortex, it is the part of our visual system that shows a lot of similarities with the first convolutional layers.
Yes.
So with the study of retina, we can think to add some convolutional layer in order to complete all the analysis given by our visual system, our
correct.
So the modeling process consists essentially of two steps. The first one, it is to build a model for the specific part of the visual system, for the cells, for example, for the photoreceptor. And then we have to model the way to transmit the signal or to elaborate the information. Then we will do this for every part of the visual system. In particular, we will pass from an anatomical description to a mathematical one. Then I will give some details on this mathematical one. For the part that regarding photoreceptor, in this image, we see the first part of retina. This is a scheme of retina, and this is a scheme of the first part. This is the hemiretinal receptor layer that is made by photoreceptor cells. And the signal transmission, it is modeled by this receptor activation field. So we can think every photoreceptor, so the one that is represented here, like a point of a compact, simply connected domain in R2, because it is essentially a surface. And then the function that transmit the signal, transmit the light hitting the photoreceptor can be thought as a function that it may not be continuous, because if we think of an image we don't have, for example, continuous view of pixel, especially near the borders. But this function has to be bounded and proportional to the intensity of light. We will give not a closed form of this function, but we have these three properties. Then we arrive to the second part of retina, that is the ganglionic layer. That is a structure made by this ganglion. And we see that a ganglion, this black ball, it is connected with a sort of circle of photoreceptor, but a circle centered in a specific photoreceptor linked with this ganglion by specific function that can be modeled like an isometry. And then we model the way in which the signal it is elaborated by this ganglionic activation field. So to point out this explanation, a ganglionic layer can be described like a compact sect in R2, like before, and we have the ganglion linked with the photoreceptor with this isometry, and then the elaboration of the signal is made by this sort of convolution. Now I want to focus my attention on this convolution. For every ganglion,
Filippo, it's not sort of a convolution, it's really a convolution.
It's really a convolution,
yes. And the other thing I also wanted to say, you have 5 more minutes, okay? So try to do 5-10 minutes.
I will accelerate.
No, I don't want that everyone should get the same time. So 5-10 minutes, you still have no more.
Okay. Oh. So we can see that we have a convolution centered in the photoreceptor linked with the ganglion, and at the center of this disk we have a sort of mean, because the function k has the value 1. So the signal arriving from retina, it is taken, and then we perform a sort of mean. But there is a zone that we call inhibition chrone, in which we have a sort of inhibition effect. So we can be robust against great light variation. And we can say that the concept that I reported here. Then we can say also that this function R is Lipschitz continuous in both variables. This can be proved, and this property encodes the fact that our visual system it is able to reconstruct border and edge. Then I will maybe skip this part, but V1 cortex it is modeled by these hypercolumns that are cells that are able to identify direction. So from a geometric point of view, they are essentially a fiber bundle, because locally they are a product space. And we have the location of the hypercolumn described by x2 prime, y2 prime, and all possible direction that scan the image. And essentially, if we define the concept of, sorry, I go faster, the concept of orientation of a function on a compact simply connected set, we can think that the edge can be identified like the orthogonal direction in respect to the gradient direction. So this is a sort of directional derivative, and performing the Armax, we find the orthogonal direction respect to the gradient direction. So in an image, these represent an edge orientation. Here, the function f, it is essentially the function f tilde, that is the electric signal that arrive from the ganglionic layer. So I will describe briefly the retinal net. I will recall the main purpose, that is to gain robustness against large variation in global light, and it is simulated by the functioning of retina. So the main idea it is to add to this LINET5, that is the classical CNN architecture introduced by LeCun, in order to gain this robustness. How this experiment was performed, both CNN architecture, LINET5, so the classical CNN, and RetinNet, that is the custom CNN, are trained on the original dataset. But then the accuracy is measured on a perturbed dataset. So we want to test how these two networks trained on a clear dataset with some ideal condition of light react to a real situation in which maybe the images are perturbed by different condition of light. So this is the LeNet5 architecture, so 2 convolution layer and 3 fully connected layer at the end. And this is the precortical module. I want to point out that in order to preserve the input data dimension, there is a precise choice of kernel size, stride, and padding, and this represent the sort of pre-processing process that it is performed by our retina. So this gives us the smoothing effect. And if we look at the 2 types of perturbation, the authors tried to perturb the dataset with a luminosity change. So they took every pixel and they shift this pixel in order to simulate this luminosity change. And then they performed a contrast change with this transformation for every pixel. So we have here the parameter mu for the luminosity change, and here the parameter sigma for the contrast change. And here there are some examples of this perturbation. So the original image plotted with this grayscale, and this high luminosity, high contrast, dark, low luminosity, and low contrast. And these are the results of accuracy for 3 datasets and for both CNNs. I will focus on fashion mist on this figure that is maybe more clear. The red one, it is the RetiNet, and so the custom net, and the black one, it is the original LeNet5. So we see that I won't go directly to the conclusion. We see that on the left we have the mu shift, and on the right we have the sigma shift. And in the case of non-perturbed dataset corresponding to mu equals 0 or sigma equal to 1, the addition of this module did not impact greatly on the final accuracy. So it is a very good thing. But RetiNet improves strong robustness with respect to the perturbed test set. So we gain this robustness against perturbation of our images. And I tried to do the same thing on the CNN that was presented us 2 lessons, and I skip all the description because we saw together the lesson. These are the results for mu sweep, and we see that the blue one, that is the original CNN, in the case of light images, it is more robust respect to the modified CNN, but in the case of darker images, modified CNN, so the CNN with this precortical model is very, very robust with this with respect to.
So you tried it. You tried it with a different model to see what it was going on. You tried it with a different CNN.
Yes, with the CNN that we saw together with
look at that. So what I'm saying in the paper really works. Okay.
Yes. So here in the case of darker image,
yes,
and in the case of sigma sweep, we don't have
not so much.
But okay. I can say that I won't be honest. This CNN, if you do the computation of number of parameter, has about more than 1 million parameter. Respect to the LeNet5 that has 60,000 of parameters. So I can think that maybe the CNN that was showed to us during lesson, it is more capable. So it finds some ways to absorb this effect of perturbation. But we can notice that modified CNN is robust. That doesn't represent a lot of variation of accuracy. So even though is in 3 cases on the 4 presented performs worse, it still follows the trend of the original CNN and show less variability.
Okay.
Thank you for your attention and sorry for too much time.
Yes, you present a lot. I'm very impressed that you did also the calculations to check our results. It would be very embarrassing if our results were not confirmed, but luckily they were. So I think now is Francesco and Elena. So I'm sorry, no questions because there is not much time. So guys, can you tell me, because I'm going to give you time. So is it like, I give you like half an hour because it's a longer presentation, or is like a same time?
No, it could be regular time.
Okay, that's fine. So I sign the time and then I will also ask a question. Please, Francesco, go ahead and share.
Professor, sorry, can you?
You are allowed to share. Yes, yes, you are. Oh, great. Spectral network sounds great.
Yeah, sounds great. Actually, we kind of knew, both me and Elena, to this kind of topics. So we tried to read this paper by Bruna, Lekun, and Dalteri and comment it in a way we try to, get more acquainted with this kind of.
They don't write mathematics; they write something else. So let's see what you did, because okay. I know how they write.
The topic is centered on the construction of spectral neural networks, spectral graph neural networks, which is based on the spectral decomposition of the Laplacian matrix.
That we couldn't do in class, unfortunately. That would be very interesting. There is a lot of mathematical topics connected with it. But let's.
So we will try it together.
Okay, let's see.
Okay, this is the outline of the presentation. So basic definition on graphs, properties of the Laplacian matrix, graph filter, Fourier transform on graph signals, then convolution, and finally the spectral construction of the graph neural networks. Basic definition: a graph is a couple VE, where V and E are respectively two sets. The set V is called obviously the set of vertices or nodes, and the set E is called the set of edges. If we have a function from E to R, the graph is said to be weighted and is said to be k-regular if every graph has the same number of neighbors. An adjacency matrix is a square n by n matrix such that is equal to 1 if two nodes are connected, or 0 if they are not. In the case of a weighted graph, the matrix will be constituted by the weights on the edges and will be denoted by W. So if D is the matrix, is the diagonal matrix which has the degree, so the number of neighbors for each node on the diagonal, we can construct a square n by n matrix which is called the Laplacian matrix. We then represent here the normalized Laplacian, both in the case of a k-regular graph and the cases of a not regular graph. Obviously, the Laplacian has some interesting properties. Is positive semi-definite. Here we can see it. If we have a vector, we've ended the number of nodes. We had that the transposed multiplied by L multiplied by F is obviously positive, is equal to this product here, and is positive. We can construct from the incidence matrix of a graph the Laplacian, multiplying the transposed by itself. And then by the usual min-max theorem, we can obviously recover all the eigenvalues and the relative eigenvectors of the Laplacian. Here we normalize, but actually it's the same thing. So this interesting theorem, which has a lot of application in both graph clustering, or in this case, as the number of zero eigenvalues of the Laplacian, the multiplicity of the eigenvalue, because being positive semi-definite, the Laplacian has all positive eigenvalues and has at least one zero eigenvalue. So the number of zero eigenvalues is the number of connected components of G. In particular, EG is connected if the second smallest eigenvalues, λ1, is greater than 0. Now we present graph filters. In general, graph signal is defined as basically a function from the nodes to R, but here we present it this way: a map on the graph nodes that assign the signal coefficient phi real to the ith node. So a graph filter on G is a graph shift that replaces each signal coefficient phi indexed by node with a linear combination of coefficient at other nodes, weighted proportional to the degree of their relation. And here W denotes the weighted adjacency matrix. This is this important result. In general, any linear shift invariant graph filter is a matrix polynomial in the adjacency matrix. And
Francesco, there is an important point here that I'm not sure if so there is something called the circulant matrix that is a shift invariant matrix. Did you look at that? No, perhaps.
No.
Yes. No. Okay.
No, yeah.
No, it's not your fault. I should have covered this, but then, you know, in the course there was no time. Write for yourself. These circular matrices are a key object for these things. And they exactly, so you can really tell how they are made in order to have this shift invariant property. And the eigenvalues, in fact, are all roots of unity. I don't know if you see this fact.
The eigenvalues are all
roots of unity.
No, I didn't.
Oh, okay.
Yeah.
Don't worry about that. Keep going. Don't worry about this. Okay.
Okay, so we can represent any shift invariant graph filter in this way, such a polynomial in the adjacency matrix. And the space spanned by the eigenvectors of the graph Laplacian, actually also the eigenvector of the adjacency matrix, is invariant to shifts. So we can represent the eigenvectors as a Fourier basis for a graph signal, basically. So given a graph signal and the Fourier basis, which are in this case are the column of the eigenvectors of the Laplacian, we can decompose each graph signal with this coefficient. And I already said it, UI are the column vector of the orthogonal matrix from the spectral decomposition of the normalized Laplacian. This is the convolution operator defined on based on graph. Here we have so we can see that each operator can be decomposing the Laplacian. We can see each filters like a product of the column of the eigenvectors of the Laplacian for a polynomial applied in the diagonal matrix, which has the eigenvalues of the Laplacian on its diagonal, which is this operator here applied to normalized Laplacian. And this is equal to a convolution between the coefficient of the spectral decomposition of these filters for the coefficient of the Fourier decomposition of the graph signal. Here we can finally construct our spectral graph network. If we have a weighted graph and U are the eigenvectors of the normalized graph Laplacian L ordered by eigenvalue, we can associate a graph with a node signal with N and CK, where N are the numbers of nodes and CK are the number of features per node, and construct each layer here with this formula, where FKIJ is a diagonal matrix, H is a real value linearity, and J goes from 1 to CK. And then I think I will leave the floor to Elena.
Yes, I will make some comments, okay, because I've read their papers, and what they do, I mean, these people, you know, Bronstein, LeCun, all these people, they use Fourier analysis and they make an analogy for this, right? This is not correct way to think about that, because we don't need Fourier analysis. L is a symmetric matrix. As any symmetric matrix, there is the, you know, spectral theorem telling us that symmetric matrix allows an orthonormal basis. And that's what the U's are, an orthonormal basis. And there is no need to expand in series. They're crazy. It's just, since it is orthonormal basis, I can express any vector using such a basis. That's all they're doing, right? So it is, and it's not difficult to prove all of this. And I'm sorry I couldn't have the time in the course to go over it, but I'm writing the notes and I will share the notes with you, okay? So that this madness that you've read, it's not the way to do it, okay? So, sorry,
right. No, yes, actually, you could decompose any symmetric matrix, or you could use the Jordan for decomposition. I've seen different articles that go in this kind of way, and yeah.
Okay.
I'd like to study more.
Okay, so I will send.
Okay, I will leave.
Elena, of course. Yes, yes.
Okay, I will not keep the video because of the quality of my connection. Sure. Okay. Okay, do you hear me? Yes.
Yes, of course.
Okay. My colleague Francesco just introduced this formula for the spectral convolution on graph. And where the Fkij are the graphs of size n times n, where n is the cardinality of omega. And these matrices contains the parameters to train at each layer. And the layers are big K, and the input vector is of size n times Fk minus 1, where Fk minus 1 is the number of features for each node of the graph. And the output vector is of size n times Fk. And H is a non-linearity applied to the vector. There are some useful remarks to say about this formula, because we see that in each layer, the number of parameters to train is Fk minus 1 times Fk times the cardinality of omega. So the complexity is a big O over n. And so it depends upon the input size. It depends upon the number of the nodes. Another remark is that often only the first D eigenvectors of the Laplacian matrix are useful in practice. So we see that in this formula, U is the matrix with all the eigenvectors of the Laplacian, but we can choose only the first D corresponding to the smallest eigenvalues. In that case, we just have to replace the matrix U by UD, which contains only the first D columns. And so the number of parameters to train will be Fk minus 1 times Fk times D, but it still depends on the number of the input size. And the cutoff D depends upon the regularity of the graph and also on the sample size of the input. Here I want to show a picture, two pictures. These two pictures show on the left 20 eigenvectors corresponding to the smallest eigenvalues from the MNIST dataset. So each element of this dataset is a 28 times 28 grid, and each eigenvector has the same size. And in the bottom left part
But
of
Elena,
the picture.
I'm sorry,
we
I
see
don't,
yes.
Elena, I don't understand the pictures. I'm sorry. So you have a 28 by 28, the MNIST, right? So
Yes.
what is this thing? It doesn't look like numbers. What is the value of the eigenvectors? I'm confused.
I think that this are the eigenvectors corresponding to an element of the MNIST dataset.
Oh,
so
I see. Okay.
I think.
Okay.
And so because the since an element is 764
Yes.
dimension, we have 764 eigenvectors.
Sure.
But here we show only 20 eigenvectors corresponding to the smallest eigenvalues.
Okay, no, I understand now. So it's not, so it corresponds to the image, but it's nothing to do with the image. Okay, thank you.
No, exactly. And on the right, we do the same thing, but using another data set. I mean, it's similar. It's just the subsampled NIST dataset where the image have the same size, but only 400 pixels are colored, and the remaining pixels are just white. And we can see these eigenvectors can be viewed as a basis in which we decompose our graph, and our graph is an image from the dataset.
No, it's clear now what you're doing. Yes, thank you.
Okay. There are some issues with the regular spectral convolutions, where regular, I mean with the formula I gave and Francesco gave at the is that the number of parameters to train for each layer depends upon the input size, and the authors wanted to reduce this complexity to big O of 1, so to make it constant, not dependent from the input size. And the other is that the graph filters also depend on the graph structure, which is encoded in the matrix U. So Bruna is an author of the article.
Sure.
So Bruna and the other authors were focused on fixing these and other issues by introducing the notion of smoothing in the spectral domain. They were the first to apply spectral graph analysis to learn convolutional filters for the graph classification problem. The filters learned using the general formula, so the formula I gave at the beginning, act on the entire graph. They are globally supported, and in general, they tried to make filters smaller and more local, so that they propose this smoothing procedure in the spectral domain. The idea, subsample set of coefficients, which are the frequency multipliers, and use an interpolation kernel to obtain the rest of the coefficients. And to do this, they took the splines, such as cubic spline. Sorry, this is okay. Were written as a sum of Q predefined functions, such as splines, and these functions are the GK. And instead of learning n values of these matrices for each filter, n is the size of omega, they just had to learn alpha k, the coefficients alpha k, which are Q for each filter. And so they wanted to approximate the filter as a finite sum of these splines. And this became very efficient when Q is much smaller than the cardinality of omega. And yes, the degree, I said cubic, but the dimensionality of this spline depends depends upon the cardinality of omega. But the important thing is that these functions are fixed, so we don't have to learn this function. We just have to learn the coefficients alpha k. So they managed to reduce the number of parameters to train from n to q, so constant and independent from the input size. But these images show, this is an image for NIST, that the filters are still large as the input size, so 28 times 28, but their effective width is small. So in this image, we see in this picture, in the left one is the input image of 7 from the NIST. The second one is a local filter train, and this is the convolution between the NIST image and the filter. So to summarize, and models with this smoothing can achieve a similar results as the model without smoothing, but with much fewer trainable parameters. To conclude this, I just wanted to show a numerical experiments that Bruna and the other authors did in the article. They considered the subsampled NIST dataset, where each 28 times 28 grid is reduced to 400 coordinates. And we remark that in this dataset, we cannot use the classical CNN because there is no regularity of the classical NIST dataset. And this is the table that show the performance of various neural networks that were trained on this NIST subsample dataset. Yes, in all experiments that they did on this dataset, they used the ReLU as the nonlinearity function, and they trained all the models with the cross entropy loss with a fixed learning rate of 0.1. As a baseline, they trained the standard nearest neighbor classifier, which gave an error, a quite high error of 4.11. So it was not very efficient on this data. Fully connected neural network, which was it is the order of 10 to error. And then this third neural network is one that it is based on locally receptive fields. I did not read all this part of the article, but it was the one that performed the best on this data set, but it required still a lot of parameters. And in the last part of the table, we can see the performance of the three neural network derived from the spectral construction. So the first one is the classical GNN, spectral GNN given by the original formula, the one of the beginning. And so we see that this D1 is the number of eigenvectors that they kept for the matrix U. So they kept just 300 eigenvectors among the 400. And the Q equals N, it means that we are not using the smoothing procedure, and we have to train all the parameters of the filters. So they are N parameters per filter. And this gives an error of 2.6, but we see that when we apply the smoothing procedure with Q equal 32, the parameters are half of the parameters of the previous one, and the error is better than the error of the previous neural network. And we see that if we enable the parameters to get very, very large, the error is the same as this neural network, but with a lot of, with less parameter, because here we have 10 to the power 3, and here 10 to the power of 4. So,
Okay.
yes, just this.
Yes.
And these
So,
are the references that we use to.
I must confess, I'm not an enthusiastic of these papers because they're not, okay, they pretend to do mathematics. I'm sorry, I'm recorded now, but they write a lot of things which, okay, I'm recorded, I won't say more. But thank you for giving this presentation. Now I think is the turn of the Ashish. Yes, you can stop sharing. It's not your fault that the presentation, you know, I don't like this type of papers. So, and then Ayub, you speak last, okay? So Devashish, please go ahead and share. You will have between 15 and 20 minutes, roughly, and I will ask a question. So go ahead.
Sorry, can you see my screen?
Yes, I do. Yes.
All right. So yeah, I'll start now. So good evening, everyone.
Go ahead. Yes. You are muted. We don't hear you. Devashish.
Oh, I'm sorry. I'm so sorry.
Go ahead. Yes.
Yeah, so good evening, everyone. And I'll be presenting a paper titled Kernel GNNs, Interpretable Graph Neural Networks with Graph Kernels, which was published last year in the AAAI Conference on Artificial Intelligence. So I'll start with the introduction of the paper and the main idea that the authors propose. So the paper presents the concept of kernel-based GNNs, which is based on the idea of using, trainable kernels functions in the graph domains, and it is actually inspired from convolutional neural networks based kernels, which help us extract important properties, in the applied cases of images, training neural networks of images. So the inspiration comes from CNN-based kernels, but applied in the graph data. So that was very interesting to me, and I hope I can apply a similar thing in my research as well. Another thing this paper is important is in the way of it addresses some limitations of the existing GNN methods. We'll get more into that, but there are two general limitations, which are the GNN methods, which is the expressive power of them, and the interpretability. But interpretability is a bigger problem in deep learning in general, so it's a very big problem. So, but this paper somewhat proposes an idea of somewhat interpretable graph neural networks, which is also interesting. And the authors also test their proposed approach on some real-world graph data and show some interesting results. In many of the cases, actually, their proposed method outperforms state-of-the-art and benchmark models. So, distances actually works in many of the cases, and specifically in node classification problems. So, and lastly, I'll talk about model interpretability, which again, this paper proposes a way to interpret the GNN architectures, which could be useful in many cases. So before going into the details, before going into the methodology, I would like to revisit, convolutional neural networks and how kernels work in that case. So the main idea behind using kernels in CNN is, you might already know, is create a higher order representation of the input data. So CNNs mostly are applied in, very popular in image-based data sets. So the idea is to, transform each pixels into a higher order representation through a convolution function with a filter. So as you can see in the image, so we have the data in the form of pixels.
Devashish, I am a bit not fully agreeing with this, because I don't view CNN as some transformation that goes from pixel, because that's not a punctual transformation. It's more like a local transformation, right? So you don't get just the information of one pixel, but you get information of that and what is around it, isn't it? Right? It's like our eye, what Filippo was telling us, right? When we look at something, it's very meaningful what is around the point, because if we just see a point, it has nothing, right? So I'm being picky. I am sorry. I'm being pedantic, but I think
no, you're right, totally.
Okay.
Like, of course, I mean, the idea of filters is to see what is around a pixel and combine all the information around the pixel as well to form a different representation.
I disagree with the philosophy of this. Says, oh, we must update the representation of a pixel. I don't see it, but it's not your fault.
I would rather say it's not a representation of a pixel, but a patch of an image. Right?
Yes,
so patch,
that's more. That feels more like it. Okay, keep going. I'm sorry to be pedantic. Keep going.
Yeah, no problem. So yeah, so the idea behind kernel graph neural networks is very similar. So think of each pixel, each node in a given network as pixel, and the idea behind using filters in graphs is similar, right? So we don't just consider each node, but the surrounding subgraph of it, and combine information from the subgraph and transform into a different representation of the subgraph. Right, so that's the inspiration behind using kernels, and kernels are actually, and this method actually helps to extract important features in the given images. So given image can be noisy, but if you apply a kernel function to it, you extract the important features to it. So right, so I'll also talk about some issues with the current GNN architectures, and because this paper actually tries to, find a way to overcome these challenges that GNNs have. So GNNs have one problem of expressivity. So in the very traditional setting of GNNs, message passing neural networks, which is the idea behind GNN architecture. So we can't differentiate between non-isomorphic graphs. For example, in the shown image, right? So if we use, they are completely different graphs, but in the traditional GNN setting, we'll just consider in the first graph, for example, we'll consider neighboring informations from 2 and 3 if we want to focus on node 1. But the proposed method, which traditional GNN will also consider the second graph would be the same, because it won't consider the edge between 2 and 3 in any way. But the proposed method actually tries to overcome this and consider, the edge between 2 and 3 also in some way. So which could be important, to understand interactions, how interactions work between subgraphs.
I'm again being pedantic. It is true that the message passing gives you the neighbors, but then, you keep repeating it. So somehow the information will filter even from far from that node, right?
True, but it's like how many. But it could be that it could take longer to converge. It could take longer number of iterations to converge.
That's true. The more you don't have many connections, because then you pay. But okay.
Right. So that's one issue of the traditional GNNs. Another thing is the lack of interpretability. Which again, I mentioned before, it's a bigger problem in deep learning in general. But, with this approach, there is one way the authors propose that we can actually find a way to interpret what's going on. in the learning process. So, that's another challenge that this paper tries to overcome that traditional GNNs doesn't. So I'll go to the next slide and give some background on graph kernel methods. So graph kernels are not new. They have been already proposed long back by researchers and also studied. So the idea is simple, like if we have two graphs and, we just try to, put a convolution function to get some important properties based on two graphs. And those graphs could be, could be anything. They could be weighted, they could be non-weighted. The important thing is the adjacency matrix we construct, and that will involve different features, different node features. In the case of so a weighted graph could also involve the edge features as well, while unweighted graph could be just one hot encoding type thing. So the graph structure doesn't matter, but so given two graphs, the convolution, the kernel method is simple, like any other function, right? So it takes the input from both the graphs and tries to construct a new representation. And one different thing that this paper tries to incorporate is the learnable filters. So instead of using some predefined filters, like we use in CNN and even GNN architectures, the authors propose why not, we learn the function itself. So they introduce parameters to the function, and those parameters are learned in one whole pipeline with the GNN architecture. So that's a novel thing that these authors have proposed and try to incorporate in the GNN setting, learnable filters. So going into the method of the paper itself, again, our goal is to construct an updated representation of the network through some transformations. We can call them embeddings, graph embeddings. Well, traditional GNNs do that, but the way they work is they have they have predefined aggregation functions. Either they consider a subgraph for a particular node and aggregate all the features around it, or they have some predefined other functions. But this paper actually tries to learn the function itself, which is important,
so
I guess.
Devashish, I have a question, because this idea of these subgraphs, it's a very reasonable, but how do you get around the fact that, it's not like a grid-like structure, right? So the neighbors are all different. That's why people are using the message passive, because convolutions cannot be done in that way. So how do you get around that?
What do you mean, like grid type structure?
So you're using neighbors-induced subgraphs, right? So morally,
Right.
what you're doing, you're looking at a neighborhood as a subgraph, correct?
Mm-hmm, mm-hmm.
Yeah. So you will probably give weights to that structure, but then it won't be the same for each node. So it will be different for each node. So I'm a bit confused on how you implemented this.
Well, I mean, yes, we look at a subgraph for each node, right? You're right. And
yes.
we have to, assign weights for that particular adjacency matrix, right?
Yes.
So consider the adjacency matrix of a subgraph, right?
Sure.
And that could be anything. That could be populated by the node features or the edge features, right? And the idea is to assign the parameters to that adjacency matrix itself, right? So instead of, fixing that adjacency matrix, okay, we start with what we have as the node features in that adjacency matrix, and then we introduce parameters to it, right? That are learnable.
Okay, I understand. Thank you.
Right. So yeah, so that's the idea. And so one benefit of using these subgraph-based filters is, it overcomes the first challenge that I mentioned before that traditional GNNs have, the power of expressivities, right? So it can distinguish, it can find a difference between, two non-isomorphic graphs, easily if we use filters, if we use multiple filters, because the function itself is trainable, right? If the function doesn't find a relevant connection in the adjacency matrix, it will just assign a very low weight to it, right? In a learned way. So yeah, that's one challenge.
This is a big problem. Understand when two graphs are the same. This is not easy to look at it, right? I think there has been recently somebody that using geometric deep learning has solved some conjectures along that direction, right? Okay, but how can you know? Okay, keep going. Sorry about that.
Okay, sure. So going into the details of the further details. I already mentioned because professor already asked this kind of question before. So what exactly filter is? So filter is, again, it's a trainable matrix, right? Just like CNN filters, which are fixed in a way, but graph-based filters are the same kind, but with parameters assigned to it. So we have a parameterized function that is part of the learning process, which with different, node attributes, edge attributes assigned to it, it just starts from that. So, right. So again, so if we have a graph and, if we have, different nodes in it, so each node itself is transformed by a kernel-based filtering method in this way. So we iterate through each node and consider subgraphs for each node, and assign and take the convolution with the subgraphs to get a different node representation for the whole network. So in a way, this the whole approach sounds exactly like standard GNNs. But one difference is how the node update works. That's the main idea behind this paper too. So standard GNNs, how they work is like, okay, we have a node and we consider subgraph of it, the neighboring connections to it, and we aggregate all the features, in some way. And those features could be anything again. While kernel GNNs is on the same idea, but instead of using a simple fixed aggregation function, it's a learnable function. So it's a parameterized function, and with this algorithm, we update each node through some filters, right? So instead of using a simple aggregation, it's like, okay, we consider the immediate neighborhoods for each node, and try different filters on it, and then reconstruct the whole network embedding. So in this way, the traditional architecture, traditional GNN is a special case if you think about it. So instead of, if we just fix our kernel, if we just define our kernel, okay, this should be aggregation function, then the kernel's GNN becomes standard GNN. So in this way, they generalize the standard GNN to be more learnable and to be more flexible. So, we talked about the theory and everything. Sorry, did you have a question?
No, I was trying to see all these databases. So you're doing protein enzymes. Where is, Reddit is the one of the houses. Is it right? No? What is?
Yes.
Okay.
So, right. No, Reddit is the online, social media. So
it's a social media. I'm sorry. Okay.
Right.
Yeah. MDB, I know what it is. Proteins and enzyme is, my students were playing with that too. So you got good. So what is your net? Oh, Kara. Okay, very good. You put it.
Right. Is the last rows. Mm-hmm. And yeah, the authors actually show that it beats many of the state-of-the-art models in this. So all these problems are, for those who don't know, it's it's like a node classification. It's a classification problem. Yeah. So we try to classify different nodes based on training the model with the given networks from each of these data sets. And kernel GNNs shows, promising results in many of the data sets. And in the other ones, when it doesn't, we have comparable performances as well. So, it shows that, it actually works. It doesn't sound good only in theory, but actually gives promising results as well.
Okay, so, right.
And one main last thing I have is about interpretability, which I also talked about before.
Yes, we're about short of time, but I mean, can you do it in 3 minutes or no?
Sure. Yeah. I can do earlier. Yeah.
Okay.
Right. So last thing is about interpretability. So there is a way of interpreting, the model itself, which many deep learning models lack. So, and how to interpret it? Well, we interpret the learned kernels, right? So suppose we have a given graph, right? In this case, it's like a chemical compound graph. So 3 atoms, carbon, nitrogen, oxygen. And we want to construct, a node representation, a network representation of it. So we deploy kernel-based GNN architecture and learn the kernels. And here we visualize all the kernels. So we see the kernels are circular in shape, which actually tells that, circular-based topology is actually important in our data set. And in this case, that means, carbon-based atoms are important in this data set. So that's the idea behind, making this interpretable, this whole thing. Right. So to summarize the whole idea of the paper, so again, the idea is to introduce learnable kernels in the whole pipeline, in the whole GNN pipeline. And in that way, traditional, graph convolution networks, which are popularized by Kip and Welling, is a special case of kernel GNNs, where we fix the kernel to simple aggregation function. And this method actually fixes the challenges we have from traditional GNNs, expressivity and interpretability in some way. And the authors experiment with real-world data sets, graph data sets, and show promising results on this. So, and these are some of the papers I found interesting. The first one is the paper itself. So yeah, thank you for listening.
All right.
Hope you find useful.
That is very interesting what you do, Devashish. And I'm glad you put all the references because, I think I want to read more. So thank you, and make sure you and also the other guys, please send me also your slides, right? Because we want to post all of this material on the website. That'll be very good. Okay, then there is the last person, Yub.
Yes.
Yes. So please, yes, start, and you have between 15 and 20 minutes, and I will also interrupt. All right. Very good, autonomous driving. So Ayub, I know nothing about it. So you are really getting me from total outside, but very excited to learn. Please go. You are muted. Ayub. Ayub, you are muted. Not so difficult. You should unmute yourself. Let me see if I can do it. Let's see. Okay.
Okay, now you should hear.
Yes,
Yeah.
we can hear you. Go ahead.
Okay, great. So now the presentation is titled Geometric Deep Learning and Observers for Robust and Interpretable Autonomous Driving Application. So basically it's due to the fact that I'm doing a PhD in mathematics computer science, but my background is more on computer engineering and autonomous driving applications. And also, let's say, my research is more on the application, mathematics computer science, more computer science application to the autonomous driving. So I will quickly introduce some deep learning approaches for autonomous driving for some tasks. Then move to the motion prediction, which is a subset of the paradigm of the autonomous driving. Then moving to the geometric deep learning for motion prediction, exactly. So how to use how there are, let's say, I will give a summary of some survey of papers that I read about geometric deep learning for this task. And then my quick, let's say, observation about possible future of deep learning neural network approaches for autonomous driving. So the most famous, let's say, task that has been solved thanks to deep learning approaches is the detection. So basically detecting other vehicles, cars, objects, agents on the road. Famous work is the You Only Look Once paper, also known as YOLO network. Is basically a convolutional neural network able to detect this kind of agent. It's quite popular and used in the autonomous driving domain. Another kind of task is what is called segmentation. So understanding what exactly some part of the images means. So not just detecting, but let's say doing a kind of clustering of the image. So in order to detect the road, of the sidewalks, objects, and so on. So this is an example of deep lab rethinking atlas convolution for semantic image segmentation. And let's say that the detection, segmentation, and also other perception tasks, so tasks related to receiving data from the sensors, so cameras, LiDAR, so sensors that emit some laser to the environment, are, let's say, can be considered almost solved. For sure, there are some improvement that can be done. For example, as Filippo said before, for example, due to lack of some light or contrast, there are a lot of things that can be improved. But let's say that can be more or less considered solved in a decent, let's say, level. But there's another task that is quite challenging, which is the prediction. So predicting the other agents, trajectories, and movement, which is still a challenging problem because there are several ways to solve these tasks. And in the past, it has been solved by, let's say, physics-based models. So basically, you know that a vehicle or agent is moving, and they simplify the concept, saying that the object has a constant acceleration, constant behavior, so it makes easy the problem, but it's not true. It doesn't let's say predict correctly the behavior. There are other approaches like maneuver-based models, where you know that an object, it can move ahead or to the left, to the right, but even in this case, it's not so accurate. And other interaction-aware models in the last decade, where what they found is that, of course, you should not predict an object by just its last actions, but also understanding the interaction to the other agents. So before, let's say, the deep learning approaches, what has been done is just to, let's say, try to connect, for example, the distances to the other object or things like that. But yeah, in the end, it doesn't work so good, let's say, good enough to do it. So in the last years, let's say 5 years, even a bit less, they start to think about geometrical representation of the traffic, which can be represented as graph. So basically, starting from the Bronstein paper, geometric deep learning going beyond Euclidean data, that have been already cited in the lectures. It can be, let's say, understood that the geometrical learning problem can be seen like characterize the structure of the data and analyzing the function of non-Euclidean domain. So basically, for example, for structuring the data in the autonomous driving domain, particularly for the prediction, so predicting other agents' trajectory, it's the case of interaction between the vehicles and other agents, and also the interaction between the agents and the road, so the lines, the lanes of the road. And about analyzing the function of non-Euclidean domain can be understood like in this let's say domain, can be understood as predicting the other agent's position or behavior given the past interactions. So that being said, I started, let's say, my research, my finding about this the geometrical, say, approaches to this task, starting to read the paper Graph Neural Network for Modeling Traffic Participant Interaction, where they basically, let's say, started to try to include the interaction between the agents in the neural network model. So basically here you can see the figure where in orange there's the ego vehicle, what is called, let's say, usually ego vehicle. So it means the vehicle that you are controlling, that you are moving, and the other agents. So basically you can create some edges, the edges that are the agents, and then the nodes that are the connection to the other vehicles, and of course also the information to the lanes. But in this work, what they saw, let's say, to make it work, let's say, make it more accurate in their in this application, is that they saw that using graph convolutional networks, the classical ones compute the next layer's features for a node from the decomposition of the neighborhood. But this cannot, let's say, cannot work very well in the motion prediction tasks, because this cannot treat the ego, so our vehicle features, differently from the neighbors. But we want to do that because we know that our ego vehicle is the one that can be moved. So basically what they do is that here H is the, let's say, the ELF layer activation, A the adjacency matrix, and that with the self connection between the nodes. So basically what they do is they removed the self connection, introducing a second weighting matrix that they defined a transformation on the ego's feature. So basically they included this information about the ego's node feature. Another thing that they do using graph attention networks in this case is that they said that in the graph attention networks, as it has been introduced by Velikovic, the attention depends only on the feature of the two nodes, adjacent nodes. But in the motion prediction task, there are additional data like the relative position between the object that is useful data to include. So basically what they did is that they augmented the attention computation, including the edge features. So in the activation function, they do not learn successive edge features, but use the position for each layer. So they add this also information. These, let's say, that are some additional things that they do in order to make it accurate and work in this particular domain. So starting from the original, let's say, definition. That was, let's say, our work. What now I will talk about is another paper that I read from the survey that I did, the ScaleNet, Scalable Vehicle Trajectory Prediction Network under random number of interaction vehicle via edge enhanced graph convolutional neural network. This basically they enhanced, let's say, the classical graph convolutional network, making some more information on the edge. So basically the normal convolutional neural network, it's based on the usual long short-term encoding and all the usual let's say layers of networks. What they did is that they included a graphical mode, a graph model of the environment of the interaction between all the vehicles, and this helped, let's say, the final part of the network, that is the one that it gives out the prediction of the future movement of the vehicles. So basically we have the previous positions and movement of the cars. We create a graph of modeling the interaction between and the movement between all the vehicles, and this gives to the network a some knowledge about the interaction. In the end, what they saw is that
So
yeah,
can
and
I
this
ask you, can I ask, how did you,
sure.
I missed, how did you build the graphical model? Is the one you described. So each car is connected with the nearby cars, is that right?
Yeah, exactly.
Okay.
Yeah, they are,
Okay,
yeah.
thank you.
I
Keep
have
going.
yeah, I have also another image that will be helpful also to
Okay,
understand better
okay, thank you.
this kind of how we can build a graphical model, which is
Yeah, this is a big problem, you know, when
yeah,
you're facing a real life problem, how do you build a graph?
exactly.
That's a big question. And with the car, you showed it, but okay, let me see how you do it.
Yeah, I will show you also
Okay.
another. I will talk also about another paper that they basically their work is basically on this kind of problem. So not on creating the network, but on how we can create the graphical.
Yes, and especially the other fact is that this is actually a problem of temporal convolutional network.
Exactly,
right?
exactly.
So this graph temporal, we are doing it with my collaborator, not on traffic, but on neurons, because we are interested in how neurons react to certain medicine. And this is the same. I mean, we do a graph with the nearby neurons, but okay, we took inspiration from these papers, by the way, this traffic one. So,
Yeah.
okay,
So
keep going. Yes, yes.
So yeah, basically, and then what's in the another representation of on this paper is that in the left side, as you can see, that's the attention process that they created. So on the edge enhancement process, but in the right side, then there's the node information that is passed by the final weight matrix that it's used in order to aggregate and gives finally some meaning and some.
This is, I'm sorry to interrupt, but this is the problem because as we have the same problem, the graph changes because the cars move, right? This is your problem.
Exactly, yeah.
Okay, okay.
Yeah, and in this case, let's say that it from the authors, it plays a big role also the weight that they added about the information, the interaction between the ego vehicles, so the one that we are controlling, and the other vehicles around. What they saw, the most important part of this paper is that what they saw is that usual, as I said before, the usual network for this tasks are basically formed by all these parts, but without this graphical modeling. So they basically have all the previous state of the vehicles, and then they include it on the network, but without giving, let's say, any information about the interaction. And they demonstrated that using this graph, so including the interaction on the network, they reduced by 30% the prediction error of the network. And this is something that, let's say, in the last years then became more interesting, and also the focus on the research on this topic.
Yes,
but as I said before, I think that due to the, let's say, the popularity of the geometrical deep learning approaches also for this kind of tasks, one interesting paper that I read, Geometric Deep Learning for Autonomous Driving, Unlocking the Power of Graph Neural Network with Common Row Geometrics. These researchers from the University of Munich, what they did is that they have this common road, which is basically a data set of planning, of traffic environment, so other roads, other cars, objects, but also what they call lanelets, so information between several lanes of the road. What they did is they moved what they said. They did some research. They found that a lot of, let's say, researchers are moving to geometric deep learning approaches, but they are wasting too much time to creating these graphs, because that's the most difficult part. So what they did is to create, let's say, a bridge, a framework between this kind of data sets to PyTorch Geometric, which is a really huge, I found a really huge tool by PyTorch in order to create, let's say, graphs. And this has really helped a lot. So basically what they did is to create a framework that moves this kind of data sets to basically graphs that can be learned, that can be used by a graph neural network. This is something really important. Here is the, let's say, a graph, a figure that I think that it's really helpful to understand better what you prof asked before. So basically,
yes.
we have here all the agents as we can see, and then we have also the time, so the previous movement of the agents and the previous interactions. So basically, it's not just the interaction between the vehicle, but it's also time varying, and this is, let's say, the most critical part, the most difficult in order to create
because you have to predict the graph also somehow, right?
Yeah, exactly. So
yes.
Yeah. So basically, and this, let's say that this work, the main focus on their cases was to create, let's say, a bridge between these two information. So the, let's say, the previous way to do, let's say, to learn a data set and use it, and then how we can bring all those huge data that we created to something that can be used by PyTorch geometric, but also by other possible tools. But let's say that all these approaches that I showed improved a lot the state of the art of the motion prediction. That's for sure. But there are, let's say, a big issue that is, as also said by other colleagues previously, it's the interpretability of the network. So trying to make it robust and interpretable also by the human, and understanding why a certain decision has been done. This is quite, let's say, important also for these, let's say, critical tasks where you can't, let's say, make a so wrong decision. And also following, let's say, the lecture from Patrizio Frosini, I was quite, let's say, interested on the fact on how he saw the things, so that there should be also some observers to include knowledge on the data to the networks. And also some relevant features. And this is the case because I can assure you that in the data sets similar to the ones that I told before, there are really a huge kind of information, but there are also some easy knowledge that us as human can, let's say, include, embed in this network. And this can enhance and improve a lot of this the accuracy of the tasks. But the issue is that in the actual state of the art, the NNS, it's quite difficult to achieve these goals. So to have to robustness and interpret what's going on. But let's say that with the new some new approaches that we read, but also like the GenioNet, so founding different representation of networks. So it could open, let's say, new approaches to make, let's say, motion prediction more suitable, but also other driving tasks that are basically at the moment ignored, because neural network can be, let's say, robust enough at the moment to make it usable. So for example, they are just used for detection, as I said, to detect something on the images, to predict, but not, for example, to control the car, so to steer, to brake the car, because it's not what, sorry?
It's very difficult.
Yeah, it's difficult, but it's not. It's also something that cannot be, let's say, interpretable. So you cannot understand why a decision can be done. But with these new approaches, can, let's say, open ways, some new ways to also this kind of tasks.
Okay.
So yeah, that's basically all from my side. I shared, let's say.
Enjoyed. I thought you were speaking of self-driving cars, which I know nothing, but you spoke about this traffic thing, which I have read.
Yeah,
yes.
I included all the cited papers on the slide, so
very good.
If you want to.
Yes. Okay, so let me stop the recording. Oh boy, how you do that? Okay.